Hello, class. So on this video, we're going to do an example where we apply the full potential of the Laplace transform. So as I mentioned, the reason why the Laplace transform is more general than the other methods that we have for solving linear ODEs is that the Laplace transform is going to allow us to work with functions, g of x or g of t in this case, which are given piecewise. Again, that is something that we can't really do with the other methods that we have, or that it is very hard to do with the other methods. So we're going to see an example of one such case. So you can think of this example as a spring mass system in which we have a forcing function and we want the forcing function to satisfy some properties. So for example, on the interval 0 to 5, you can think of t as seconds. You can say, okay, I want a forcing function that's forcing no oscillation, so having no forcing on the first 5 seconds on which this system or spring mass system is running. Then as soon as we hit the 5-second mark, I want to force oscillations satisfying the form 1/5 times t minus 5. But I only want that for the 5 to 10 second mark. Then at the 10-second mark, we force a constant function oscillation of 1. Okay? And this is very common, in fact, in a lot of applications where you have different sort of forcing functions on different intervals, right? So in a case like that, it's very convenient to work with a Laplace transform. Okay, so now that we've gone over that, we're going to try to solve this problem. Now, as I mentioned, you could integrate or find the Laplace transform of g of t by just integrating an improper integral, right? Just separating the intervals into each respective domains, right? So you would integrate the function 0 from 0 to 5 and then times e to the negative st, right? The same on 5 to 10, you would integrate e to the negative st times 1/5 t minus 5. And then on the interval 10 to infinity, you would integrate the function e to the negative st. And so you could do it like that. But again, the whole point of introducing step functions was to allow us to take Laplace transforms of piecewise functions in an easier way, but in which we don't have to compute so many integrals. So let's try to apply that process to this example. So we're going to use the Laplace transform process. So we're going to take the Laplace transform of both sides, right? But first, let's try to write g of t as a sum or difference of step functions. So let's see how we can do this. And let's try to do it domain on domain, right? So first of all, on the interval 0 to 5, it seems to be matching what we want. Remember, for a step function, we want it to start as 0, right, on some interval and then switch on another interval as soon as it reaches a particular t value. In this case, t equals 5. So this thing matches the start of a step function. Let's see what happens if we include the other part of the domain. Now, this is saying that at t equals 5, we want the switch to turn on and become the function 1/5 times t minus 5. Now, notice that this has the right form as what we need, because this looks exactly like the function 1/5 t, but shifted 5 units to the right. Right? You would get this. Right? So this time in which you switch the function on matches the shift in the function, right? So we know that at least this first part we can write as a step function, right? And if you remember the formula, right, we can write this first part, and let's write it as h of t, right, u5 of t times the shifted function inside the piecewise definition. Right? So this kind of takes care of the first two parts of the domain. However, we cannot leave it like this, because this would be saying that we want this function g of t to be equal to 1/5 times t minus 5 for all t from 5 to infinity. Right? But we want it to stop at t equals 10. Okay. So let me make this more clear to read. Okay. So we want it to stop at t equals 10. So how can we deal with that? Well, all we can do is do something like this. What if we could write, and I'll explain my reasoning for this in a moment. Actually, let me use a different color. Right. What if we could write our function g of t as, okay, so the first part would be just what we wrote above. Okay. Now, we know that something has to happen at the 10-second mark, right? If you think of this as a spring mass system where t is in seconds. Now, we know how to make something happen at t equals 10 seconds, right? We can just work with the step function u sub 10 of t. Now, this is saying that at t equals 10, something else is going to happen. We're going to be subtracting something to this first part that we found. And remember, the first part is defined by this function, right? But t going all the way to infinity, right? So by me subtracting u sub 10 of t, I'm saying that, okay, at the time t equals 10, I want to change what happens. I want to change my function 1/5 times t minus 5 to be something else. And that something else is going to be determined by some other unknown function. Let's call it f of t. Okay. Right, so the idea is, again, at the time t equals 10, I want to introduce a new function, f of t, right? And ideally, the difference of 1/5 t minus 5 times f of t simplifies to 1. Okay. So that would be our goal, where f of t satisfies that. Well, what does it have to satisfy? Well, we need 1/5 times t minus 5 minus f of t to be equal to 1, right? Because we want the function to be, g of t to be equal to 1 for t greater than or equal to 10. And this is the idea. Now, notice that this works because, again, I already said it, but let me just write it. For t greater than or equal to 10, what is g of t as we have it right now? By definition, g of t is going to be this. Right? Why? Because u sub 10 of t is 1 on this interval, and so is u sub 5. Right? So that's the idea. That's how we can control what's going on. Right? By adding more terms, right, in particular more step functions or just step functions, with a parameter that we're going to solve eventually. And this parameter is going to be controlling what we want our function g of t to be in this case, in this particular interval. Right? And that's the idea. Now, notice that I'm subtracting f of t because I'm pretty sure I'm going to have to subtract something from 1/5 t minus 5 to make it equal to 1. Right? So that's why I write minus f of t. But now that we have this, we can just solve for f of t. Okay. So let's solve and see what we get. So let's use color blue. Right, so we subtract 1/5 t minus 5 from both sides and then multiply by -1. So that's step by step. So negative f of t equals 1 minus 1/5 times t minus 5. And then multiply by -1 on both sides. So this would be 1/5 t minus 5 minus 1. Now, I'm going to simplify this a little bit, right? Because remember, we want a function f of t that looks like, right? So we want, let me make a note of this before I simplify so you understand why I'm going to simplify this a little bit. We want f of t to look like a function shifted 10 units to the right. Why? Because by theorem 1 in this section, is it this section? Yeah, in section 6.3, what do we have going on? Well, we know that we can easily take the Laplace transform of a product of a step function with a function that's shifted by what amount? The same amount as the c in the step function. So since we're going to take the Laplace transform, so let me go back to the example. Since we're going to take the Laplace transform of this whole thing here, if f of t doesn't look like a function that's shifted 10 units to the right, it's going to be very hard, because then we would have to find, or basically just have to use an integral, which we're trying to avoid, to compute the Laplace transform of u10 of t times f of t. But if we can write f of t as a function that's shifted 10 units, then we can simply use theorem 1 and get this simple Laplace transform formula. So that's the idea. So as it is right now, the function f of t doesn't look like a function that's been shifted 10 units to the right. So I'm going to try to get it in that form. And so that's the idea. Okay. So let me simplify. I'm going to multiply everything out. 1/5 minus 5 times minus 5 is minus 1. Minus 2 is minus 2. Now, this still doesn't look like a function that's been shifted 10 units to the right, unless I factor out the 1/5 out of everything. Because now if I factor out the 1/5, I get 1/5 times t minus 10. And now this function looks like a function that's been shifted 10 units to the right. And it's the same function as before. So this looks like the function 1/5 t, where it's been shifted 10 units to the right. And that would be the corresponding algebraic transformation. And now our f of t matches the u sub 10 of t, right? It's been shifted 10 units to the right. So now we're done, right? Now we have the first term as u sub 5 of t times some function shifted 5 units to the right, minus the second term being u sub 10 of t times a function that's being shifted 10 units to the right. Okay? So let's write our final g of t. And then we're going to take the Laplace transform of both sides. Now, this process is faster than what I'm doing. Of course, I'm explaining everything, so that's why it's taking a little bit of time. But in practice, it's a little bit faster, right? Sometimes it might be hard to do this last step where you convert your function into something that looks like a function that's been shifted. But for the most part, you're going to be fine. Especially for the problems in this class, it should be fine. Okay, so what's g of t? It's u sub 5 of t times 1/5 t minus 5 minus u sub 10 of t times 1/5 t minus 10. So now let's take the Laplace transform of both sides of the ODE. Right? And I'm going to do them separately just because I think it's going to take it's going to be a long horizontal line. Right? So let's do it on the next page. So let me write the ODE again. So y double prime plus 4y prime equals g of t. And then we had initial conditions. And I think they're both equal to 0. I'm going to check. Yep, I think I have it all correct. Okay. So as I mentioned, now that we've written g of t in terms of unit step functions, that Laplace transform is going to be easy to compute. Right? So let's compute the Laplace transform on both sides. And so for the left-hand side, we have the Laplace transform of bilinearity, y double prime, plus 4 the Laplace transform of y prime. We have formulas for this. And this is equal to, so the first part is s squared times the Laplace transform of y, minus s, y of 0, minus y prime of 0, plus 4 times the Laplace transform of y, which is big Y of s. Now, all of these initial conditions are 0, right? So this just simplifies to, and I'm also going to factor out the y of s immediately. So this factors to, or simplifies to, s squared plus 4 times big Y of s. Okay, so that's the left-hand side. Now let's do the right-hand side. Right, so we're taking the Laplace transform of g of t, which we wrote as a difference of step functions. Now by linearity, right, we can separate this, move the constants outside. So this becomes 1/5 the Laplace transform of u sub 5 of t times t minus 5 minus, minus the Laplace transform, and I can move out the 1/5 here as well. So minus 1/5 the Laplace transform of u sub 10 of t times t minus 10. Now these we can go immediately and see our formula. Because what's our formula? The Laplace transform of the product of a step function with a function shifted the same number of units to the right is just, well, you get an e to the negative cs on the top as the first term. And then you have the Laplace transform of the original function f without being shifted. Okay. So let's apply that to this example. So this is going to be the 1/5 stays there. Right? So if we get first a term, e to the negative cs, in this case c is 5, so negative 5s, times the Laplace transform of the unshifted version of the function. Right? So the unshifted version is just t, because t is the function that was shifted 5 units to the right. We know that the Laplace transform of t is 1 over s. So this just becomes times 1 over s. Let me try to make my 5s more distinct. I should have chosen another number instead of 5. And then the same here, this is minus 1 over, yeah, so see, I'm already thinking that it looks like an s. So minus 1/5, again, using theorem 1, we get an e to the negative cs, where c is 10, times the unshifted version, the Laplace transform of the unshifted version of this function. Again, this is the function t shifted 10 units to the right. So the unshifted version is t. What's the Laplace transform of t? It's again 1 over s. Let me do that as a product. Okay. Now I'm going to simplify this. I'm going to factor all like terms, and I'm going to get a 1 over 5s times what's left over, e to the negative 5s minus e to the negative 10s. So if we combine both things, right, so combine both sides of the differential equation after we've taken the Laplace transform, we get s squared plus 4. Oh, oops, I think I made a mistake, right? The Laplace transform of t is 1 over s squared, right? So I was thinking of the Laplace transform of 1. Yeah, so thankfully I'm going to give you the, this theorem with all the Laplace transforms. Where is it? Yeah, I'm going to give you this theorem, so let me double check. Yeah, so I was thinking of the Laplace transform of 1. Okay, so good thing I caught that. Right, so it should be an s squared here. Okay, other than that, everything looks good. Y of s equals 1/5 s squared times e to the negative 5s minus e to the negative 10s. Okay. Finally, well, not finally, but almost finally. So the second step after you've taken the Laplace transform of both sides is solve for y of s, big Y of s. Right, so it's going to be 1/5 s squared plus 4 times s squared times e to the negative 5s minus e to the negative 10s. Okay. So now comes the, you could say, harder part. Right? Now we actually have to take the Laplace inverse of both sides, okay, in order to get y of t. So it's actually not going to be that hard. We're just going to use linearity, and we're going to use theorem 2. So let's try this. So y of t is going to be equal to the Laplace inverse of y of s, which is going to be equal to, by linearity, what's going to happen. So there's a 1/5 here coming out. Again, let me try to make that more like, more like a 5, not an s. Laplace inverse of e to the negative 5s on the numerator over s squared plus 4 s squared on the denominator minus 1/5 the Laplace inverse of e to the negative 10s over the same denominator. Okay, so s squared times s squared plus 4. And then what's the goal? Then it's just find the Laplace inverse of both terms, right? Now, I'm just going to do one of them for the sake of time because the other one is basically the same thing. It's the same process. So let's say we find this part here. Let's focus on that part. Okay. So we're trying to find the Laplace inverse of, and let me rewrite it in a way that looks more like the theorem that we're going to use. So e to the negative 5 times s times 1 over s squared times s squared plus 4. Okay. Now, why do I write it like this? Okay. I want to use theorem 2. Wait, is it theorem 2? Sorry, theorem 1. Right? Why? Because I have a formula for the Laplace inverse of an exponential e to the negative c times s times big F of s. Right? I have a formula for that. What is that equal to? It's just a step function. And so this is what's underlined in red here. It's equal to just a step function turned on at c and the shifted version, f of t minus c, right, of whatever function f of t has a Laplace transform, big F of s. So in other words, what we have to do here is, so by theorem 1, all we need to do is we need to find a function f of t such that the Laplace transform of f of t equals 1 over s squared times s squared plus 4. Right? Once we have that, y of t is going to be equal to, oh, sorry, not y of t, but this Laplace inverse. So let me just call this whole thing like asterisk. By theorem 1, this is going to be equal to, right? So so u sub whatever c is 5, right? Because it's negative cs, so c is 5 of t times this function f of t that we're going to find, just shifted 5 units to the right. So really the meat of the work here is going to be to find this function here. Right? Some function such that this is true. Actually, it looks pretty bad. So let me just circle it or underline it. Right, so this is going to be the hard part. This is the goal. Once we have that, we have the formula for the Laplace inverse. Now, this doesn't have the form of anything. If you look at our formula sheet in, so theorem 2, wait, no, not theorem 2. I think it's 6.2, theorem 6. Yeah. So what we have, we have 1 over s squared times s squared plus 4. That as itself doesn't have the form of anything. But if we write it as a partial fraction, then it does, because it would have a over, or some expression over s squared. And that looks a lot like just the Laplace transform of t to t squared, or sorry, of t, plus b, or some expression, over s squared plus 4, right, which looks a lot like the Laplace transform of sine of kt. Okay. So that's the idea. We're going to have to use partial fractions for, oops, this is the next section, partial fractions for this part. Now, for sake of time, I'm going to skip the partial fractions decomposition, right, but I'm going to write the work. Just what you get. So you can actually, after you do partial fractions, you get that 1 over s squared times s squared plus 4. Let me write that one more centered. Is equal to, let's see, what was it? So 1/4 over s squared minus 1/4 over s squared plus 4. Now, again, like I said, we're almost done. We take the Laplace inverse of both terms. So let's say blue. Right? So Laplace inverse, remember, our goal is to find this function f of t, whose Laplace transform is 1 over s squared times s squared plus 4. That's the same thing as taking the Laplace inverse of this expression and see what you get. So by linearity, we get 1 over 4, 1 over s squared. We know what that is. Minus, here, I want to write it in a way that looks just like the sine, right? The Laplace transform of sine of kt. So since we have 4 on the bottom, that's 2 squared, right? So our k has to be 2. So just multiply top and bottom by 2. So if we do this, we get a 2 and a 1 over 8, right? So minus 1 over 8 Laplace inverse of 2 over s squared plus 4. Right? And again, we know what this is. This is just sine of 2t. So putting it all together, we get that f of t, which we were looking for, is 1/4. Laplace inverse of 1 over s squared is t, minus 1/8. Laplace inverse of 2 over s squared plus 4 is sine of 2t. And then putting it all together into this part, right? So which implies that the Laplace inverse of star, the original thing we're trying to find, is equal to u sub 5 of t times f of t shifted 5 units to the right. So 1/4 t minus 5 minus 1/8 sine of 2 times t minus 5. And that takes care of this term here. Remember, this is star. It's the same as this one here. And then again, you do something similar. You already have the partial fraction decomposition. Right? So just do the same thing for this other part. So I'm just not going to write it down, but it's almost the same thing. Right? And that's the work. We didn't have to compute any integrals. Right? We did have to do a little bit of work to get our function g of t in the right form, but again, it wasn't that much. It just took a little bit of time because I was explaining everything. Right? And then taking the Laplace inverse, you have to do that anyway. Right? But assuming that your functions look nice and match the forms that you have, you see that it's not that hard, right, to actually compute. Okay? And let me mention, and I think I said it at the start, but this is actually section 6.4. Yeah, so basically section 6.4 is just applications of this or an example. So I just took one example from there and we went over it. Okay. Now on the next video, we're going to start on section 6.5. It's another sort of common situation that happens in a lot of applications. So I do want to cover it. Then if I think we should still have time, we're going to cover convolutions of functions. Right? So what that is. And then that should be most of the material, or at least that's going to be the material in which you're going to be tested on, I believe. And then I'm just going to do a couple for next week, I'm going to do a couple of just topic videos, which are not required for the exam, but I do want you to see, right? So you can see other ways in which you can solve ODEs and other things that arise, right? So maybe I'll try to talk about using power series to solve ODEs, and also, if I get time, also talk about systems of equations of ODEs, right? So not just trying to solve one ODE, but more than one ODE simultaneously. So how do you do things like that?